So when we're drawing these skeletal structures, there's a number of things we have to do first. So one, got to figure out how many carbons are in a row. So what's the longest number of carbons you can make in a row? And we'll find out that it's not always as simple as it looks. In this particular instance, it's pretty straightforward. I just have butane here. So I've got 1, 2, 3, 4 carbons in a row. So then I just draw the bonds between the carbons. 1, 2, 1, 2, 3, 4. And then, are there any non-carbon hydrogen bonds? No. So I'm done. So that would be the simplest way of showing that particular molecule. Now, on the other hand, for number 2 here, there's something else going on. This, I look and see what's the most number of carbons in a row I can make. So 1, 2, 3. So I go 1, 2, 3. And then, are there any non-carbon atoms, non-carbon hydrogen atoms? Yes, there are. There is an oxygen and a hydrogen bound to the second carbon. So I draw the hydroxyl group there. Now, you do not include lone pairs. So you don't have to put the 2 lone pairs of electrons on the oxygen. Those are assumed to be there, so we don't have to draw them. So these should be, in fact, easier to draw than Lewis structures, where you actually have to put all the electrons in. Here, we don't have to do that because we want to make it as simple as possible. Because usually when we're drawing these skeletal structures, we're drawing these huge molecules. And if we were to put, lone pairs on every atom that had them, it would just be way too complicated to look at. So the whole point of drawing these skeletal structures is to keep it simple. So this is all the information we need. This carbon has only 1 bond to another carbon, this one here. So it would be bonded to 3 other hydrogens. This carbon is the same. It only is making a single bond to another carbon, so it would be bonded to 3 other hydrogens. This one in the middle is bonded to a hydroxyl group, and so we would assume it's also bonded to a hydrogen to make the total of 4 bonds. But we don't have to draw them because basically we know they're there. Let's look at an example. So basically we just did this one. So this would be pretty simple to do. So butane. So remember, every line is a carbon-carbon bond. So we basically start low and go, start low and go up. So I start down here and then go up. So that already I've got 2 carbons. Then back down 3, and then back up 4. So if there's nothing else there other than hydrogens, I am finished, basically. And so this is pretty much the simplest way to represent butane. That tells you, since they're all single lines, that they're all single bonds. We'll find out later that if there's a double bond, we would just put another line there. And if we had a triple bond, we would put another line on the other side. But since these are all single bonds, we just have single lines. Now, this is also the other one I don't know why we bothered with this, because we just did them. So this is called isopropyl. And the reason it's called isopropyl is because 3 carbons is propane, right? So 1, 2, 3. But this has a substitution on the second carbon. So an isopropyl group is basically a carbon that's also attached to two others, like this. This would be an isopropyl group attached to a longer chain. So this is also called isopropyl because it looks like that, but it has the substitution on it. So the substitution is on carbon number 2. 1, 2, 3, that's carbon number 2. So we draw the bond to the oxygen, and then that's it. We do include the hydrogen if it's attached to an oxygen or a nitrogen. It's because we want to show that this particular oxygen isn't an ion or anything like that. Because since we're not including electrons, we don't know whether this oxygen would be actually 1, 2, 3, 4, 5, 6, whether that would be negatively charged because we don't show the electrons. We would be able to see if it was double bonded to carbon, we would just put another line there and then leave out the hydrogen. And we would just assume that it would have its normal 2 lone pairs. But since we can't tell whether it's an ion or not, we include the hydrogen to let you know that that's not a negatively charged oxygen. It actually has a hydrogen attached to it.
If, for example, for that question, if instead of the O, there was still, a C for carbon, would it still be isopropyl?
I think we have a molecule like that. Actually, I think we have a molecule like that in the workshop tonight. So
Oh,
you'll actually have be looking at that one.
okay.
So here's a typical example. This is an alcohol. Why is this an alcohol?
OH.
It has an OH at the end. Yeah, it has an OH group. So we call that an alcohol. So what is the longest stretch of carbons in a row we can make from this?
4.
4, right. 1, 2, 3, 4. That's my longest stretch of unbroken carbons. So I go 1, 2, 3, 4. And I see that 2 has a substituent on it. 2 has what we call a methyl group. CH4 is methane. And if we remove one of the hydrogens and replace it with a carbon-carbon bond, we call it methyl. Same with ethane, we would call it an ethyl group. So that is a CH3. And there's 2 ways of doing this. Either way is fine. Some just like to put a straight line and just assume that anytime you have a straight line, it means a carbon-carbon bond. Other people like to actually put the methyl group there. Either way is fine. Okay. And then there's another substitution. Which other carbon has a substitution on it?
There's an OH at the end of the
So a
fourth
carbon number what?
4.
Number 4, which is this one. So then we just put the OH there. You don't have to make another line, because if you make another line, remember, line means carbon-carbon bond. So we don't put a line there. If we don't have to put a line there, we don't. We only put a line if it's in the middle, like one of these carbons, like either this one or this one. If it's one of those 2, we put a line in and the hydroxyl group. If it's at the end, we just put it at the end. Okay, so that would be 1, 2, 3, 4. So we would call that butanol because it's butane. It's got and we'll deal more with these when we deal with like alcohols and other things in the next coming chapter. But when it has a OH group, if it's an alcohol, we would call that butanol. And we would call it methyl butanol. We'll deal more with we'll get into naming in a minute. All right, here's our second molecule. So what's the longest number of carbons in a row that this one has?
4.
4, right. 1, oops. 1, 2, 3, 4. So 1, 2, 3, 4. And which carbon has a substituent on it?
Carbon 1.
Carbon 1. So we would just, and this is carbon 1. So we'll just put a bromine there. If it was carbon 2, I'd put a line up to the bromine. For carbon 3, if it was carbon 4, also I'd just put the bromine at the end. So we would call that 1, 2, 3, 4. This is butane again. It's a butane because they're all single bonds between the carbons, all singles. So butane. And we would say it's 1 bromo butane, because you have to tell where the substituent is. And if it's bromine, we replace it with bromo. We'll see that. We'll see those rules in a minute. All right. So if we were to draw a Lewis structure for this one, what's the longest number of, what's the length of our carbon chain?
6 carbons.
6, let's see, 1.
Wait.
Oh,
Sorry, 5.
right. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Now, which carbons have substituents on them?
2 and 3.
2 and 3. So I have a chlorine there, and I have a chlorine there. And then everything else would just be hydrogens. So then you just fill in.
You still have to draw the hydrogens, right? Like if you ask.
If it's a Lewis structure, then yes.
Okay.
If it's not a Lewis structure, then no. And so we would call this, since it's 1, 2, 3, 4, 5, that's pentane. And we would say it's 2, 3 dichloropentane, because it has 1, 2 chlorines on it, and the positions are 2 and 3. Now let's look at the next one. So what's the length of my carbon chain this time?
Five,
What is it?
5 carbon.
5, right. 5 in a row. So 1, 2, 3, 4, 5. And then which have substituents on them? Which carbons have substituents on them?
1 and 3.
Ah, you read ahead. How come you didn't say carbon 5?
Because we always need to put 1. Or the-
Excellent. That's
Yeah.
right. Excellent. Yeah, we don't always, we want to put the substituents with the lowest numbers possible. So instead of calling this one carbon 5, we actually refer to it as carbon 1. We actually start the naming in this direction because that gives us lower numbers. Excellent job. So there's a bromine on carbon 1. And who else has a substituent?
Carbon 3.
Number 3. So 1, 2, there's 3. So carbon 3 has a methyl group. And then the rest, you just fill in the hydrogens. And like I said, you can just put CH3 on the end if you want. I will not get upset by that. So excellent job. And so we would call this, since it's again 5, that's also a pentane. And we would say it's 1 bromo to 3 methyl pentane. So again, each carbon atom, we're talking about alkanes, each carbon atom is bonded to the maximum number of hydrogen atoms it can, except for, substituents, if it has a chlorine or an iodine or whatever. Other than that, it's the maximum number of hydrogen atoms. And that's why we call it saturated, because all of its bonding is saturated. It doesn't have any double bonds or triple bonds. So every carbon is making 4 bonds. That's the indication of saturated. We can also make rings. And so we call these cycloalkanes. They're just in a circle, well, not really a circle, but they're in a ring. And so the very smallest number we can make is 3. But you really don't see that in nature very often, because we know that each carbon wants to have a tetrahedral shape. And that particular structure basically keeps the carbons too close together. So there is a lot of strain in this particular compound. And so it's really unstable. So you add just a tiny bit of heat to that, and that just breaks apart. So rings of 5 or 6 are the most common, because you don't have as much ring strain. You can see here that, that these bond angles are not ideal. We're making 60-degree angles here, when in a tetrahedral, remember, it wants to make 109.6-degree angles. So that is a lot of stress and strain. So once we make bigger rings, we can increase that bond angle and get it back to normal. So other families of compounds are called unsaturated, as we mentioned. Alkenes have carbon-carbon double bonds. Alkynes have triple bonds. And the aromatics, basically that's a whole other branch of organic chemistry all by itself. It's just aromatics. Now what aromatics are these ring structures that have alternating single and double bonds, which makes for a very special kind of compound. Because if we look at, and I'll talk more about this when we get to it, but we know that single bonds are longer than double bonds, right? So a single bond will be this long and a double bond will be this long. So if you looked at this ring, you would think that this bond, this double, and this double bond would all look like that. And the single bonds would all look like that. But experimentally, every one of those bonds is exactly the same length in between. And so this is a very special structure, and they share electrons in a very special way as well. And another thing about these aromatic rings is they're all flat. They're basically these two-dimensional, very flat structures. And so they can insert themselves. Why they're dangerous, you asked earlier, why they're dangerous is they can insert themselves into DNA rings. The rings of bases in your DNA also contain aromatic rings. And so they are flat. And so these rings can insert themselves in between the bases of your DNA and cause genetic damage. And that's basically how they cause cancer. But like I said, we'll talk more about that a little bit later. So how do we name these things? So IUPAC, I'll sort of mention that. Basically, it stands for the International Union of Pure and Applied Chemists. So basically all chemists, those either working in the lab or those just doing calculations, have come up with a naming system. So any alkane that doesn't have their carbon atoms just in a single continuous chain, as I mentioned, those are generally called N, if they're in a single continuous unbranched chain, are called branched chain alkanes. And so there are names to be given for each one of these things. And basically we start with, what's the longest number of carbons in a row? That'll be the basic name we give it. What's the suffix? Is it an ane because it's a alkane? Is it an ene because it's an alkene? Or is it an ine because it's an alkyne with a triple bond? And then we just basically put all the substituents or attachments at the beginning. So what are the attachments? What's the longest chain of carbons? And then does it have double, single, or triple bonds in it? So let's go through a couple. So here's one here. So we want to find what is the longest chain of carbons we can make in a row. So have a look, because there's actually two ways to look at this. What's the longest number of carbons?
3.
In a row. Right. So we can look at these three, and this is the substitution, or we can look at these three, and this is the substitution. Notice that each of them make exactly the same molecule, interestingly. So since it's 3 in a row, then it's 1, 2, 3. We call it propane, because they're all single bonds. And then we would name where the substitution is. And we can see that it has a methyl group. As I mentioned before, CH4 is methane, but when I remove one of the hydrogens and then attach that carbon to a backbone, it becomes methyl. Same thing with ethyl. Ethyl is just attached to a backbone. So an ethyl group has 1, 2 carbons on it. A propyl group would have 3. A butyl group would have 4, pentyl 5, and so on. So 1, 2, 3. We see it's connected to the second one, but really that's the only place it could be on 3 carbon. Because if we put a methyl group there, we've just basically made the chain one longer. If we put a methyl group there, we've made the chain one longer. The only place we can put a branch in a chain of 3 carbons is in the middle. So that's why it's at carbon 2. And so there's 2 ways. Oops. There's 2 ways to name this. And you can see that there's basically, it's always going to be carbon 2, because if we name them in this direction, it's the second carbon. If we name them in this direction, it's the second carbon. So we call it 2. That's where the substitution is. What is the substitution? It's a methyl group. And what is the longest chain? 3. So it's propane. Now, you don't have to include the 2, because the 2 only in this particular instance, the 2 is the only place the substitution could be. So actually just methyl propane would be fine, because it's assumed that if there's only 3 carbons, if you're adding more carbons to it, you'd have to add it in the middle. But usually you include the number. So separate numbers and words, we separate them with a dash there. So you can either put this as 2-methyl propane there, or you can also call it 2-methyl propane. Either one is fine.
If we
That's
didn't,
your question.
whether or not we put the 2 or not in this example, it would still be marked right, correct?
That's
If we
right.
didn't have the 2.
But
it'd
be
fine.
careful leaving that number out.
Right,
because that really only counts for adding carbon-based substitutions. And then again, only in certain circumstances. So if you don't know whether you should or not, include the number, because then you won't be wrong.
okay.
This is just one particular example.
I think Dylan has a question.
Okay.
Where did the 2 come from again? I'm so sorry.
Oh, 2, because it's on carbon number 2.
Oh.
Yeah, so that doesn't refer
Yeah.
to the number of methyls. If you have more than one methyl group, then you would put dimethyl or trimethyl
Yeah,
or tetramethyl.
That makes sense. That makes sense.
But the number refers to the number of the carbon. Where is it? Where do you find it? And then the number of substitutions. And so we'll deal with this in a second too. The number of substitutions tells you how many different methyl groups, how many different ethyl groups are there. So yeah, the very first example I can show you right in the very next slide here. So here, what's the longest group of carbons in a row I can draw?
4.
Or
4. 1, 2, 3, either 4 or that one's 4. Doesn't really matter. One of them is going to be 4. So that is what. So what do we? And they're all single bonds. So what is my base name?
butane.
Right. So I know I've got a butane here. So where are the substituents?
Carbon 2 and 3.
Carbons 2 and 3 have substituents. That's right. So there's something else attached to number 2 and number 3. So I would put 2, 3, and then what are my substituents? Since they're just a single line, what does that refer to?
Methyl.
Methyl, right. So that line is just basically pointing to another carbon. And like I said, you can draw it this way, or you could also draw it like that. Some people just like to do that. In fact, I like to do that because sometimes it can get confusing with the line like that. So I generally will put the methyl there. Either way is acceptable. So and how many methyl groups do we have total on this molecule?
2.
There's 2 of them, right? There's one here attached to 2, and there's one here attached to 3. So we would put 2, 3, telling us where the methyl groups are, and then what will we call it?
Dimethyl.
Dimethyl, right. Dimethyl, excellent. Dimethyl butane. Because it tells, so this gives us all the information we need. So we have 4 carbons in a row, and it's saturated. However, there are 2 methyl groups, di. One of them is attached to carbon 2, and the other one is attached to carbon 3. Great job. All right. Okay, now here we have something a little bigger. So what's the longest chain I could make with this one?
5 carbon.
5.
5. Right. So one, oops, let me draw that again. One, 1, 2, 3, 4, 5. Now, we could also have gone 1, 2, 3, 4, 5, but this would have given us this group here, which is a little tricky to name. So just for simplicity, we'll just go 1, 2, 3, 4, 5 right across. 1, 2, 3, 4, 5. Okay, so if I've got a base of 5. So what do we name it if it's got 5? And it's all saturated.
Pentane.
Pentane, right? They're all single bonds, and there's 5 of them. So remember, the pentathlon has 5 events. The heptathlon has 7, right? Yeah, 7. So pentane. Where are the substitutions on this particular molecule?
3 and 4.
3 and 4. Now, remember, we want the numbers to be the lowest possible.
Wouldn't it
So
be
should
2
we-
and 3?
So what should we call them?
Wouldn't you flip the 1, 2, 3, 4, 5 opposite? So you'd count it from right to left.
That's excellent. That's right. So instead of calling 3 and 4, we would start there. 1, 2, 3, 4, 5. So this way, my substitutions are at 2 and 3. Excellent job. So what's my substitution at 2?
Methyl.
Methyl. That's a methyl group. CH3 is a methyl group. So I have 2 methyl. What's my next substitution? Where is it? We know it's at 3. So 2 methyl, 3. And what's this? What do I call that? It's got 2 carbons in it.
Ethyl?
Ethyl, that's right. So that if it was completely saturated with hydrogens, we would call it ethane. But since one of the hydrogens is removed and replaced with a carbon-carbon bond, we call it ethyl. Back in the olden times, at gas stations, you may have seen like old pictures of gas stations where instead of gas, it has ethyl. Has anyone ever seen old pictures of gas stations like that? Probably, probably not. Before my time too. This is like back in the 40s and 50s. And it was because long chains with ethyl on them tend to burn better. And so different oil companies would brag about how much ethyl substitutions on their octane there was, because it burned better. So they'd say, fill it up with ethyl. So here we have 2 methyl, 3 ethyl, pentane. Excellent. Now, so sort of the last group here, we just call them haloalkanes, also known as alkyl halides. So an alkyl group is basically something like that. Something that has a carbon bound to something else. And so we would call this an alkyl group. Alkyl, just like methyl, ethyl. Alkyl means like basically any length of carbon chain substituted on something else. So either we can call it an alkane with a halogen attached to it, or we can call it a halide with an alkyl group attached to it. Generally, we'll call them haloalkanes for simplicity. So fluorine is referred to as a fluoro, chlorine is chloro, bromine is bromo, and iodine as iodo. And we basically use the same rules as we did for naming the other compounds. Now, naming cycloalkanes, when we have a structure like this, so the ring serves as the parent name, as long as it has more carbons than anything bound to it. So this has, how many carbons in this particular ring?
6.
How many?
6.
6.
Still can't hear you.
They
6.
said 6.
6, right, there's 6. So unless there is something with like 8 or 7, 8 or 9 carbons bound to it, this is the parent because it has more carbons in it. So then you identify where the substituents are. And if there's only one substituent, we always refer to it being at position 1. So if there's more than one substituent, the first one will be at 1, and then you go from there. So you never have like 2,3 dibromo cyclohexane, for instance, because the first substitution always has to be at carbon 1. And if it's a single substituent, you don't even bother saying 1. It's just assumed that's where it is. So if I had something like this with hexane and a chlorine there, I would just call it chlorohexane, because the assumption is it's bound at position 1, so you don't have to say it. If, on the other hand, there's more than one substitution, the first one will be at 1, and then you go from there. So if we have a chlorine here and a chlorine there, we wouldn't go 1, 2, 3, 4, 5, 6. We would go the other way, 1, 2, 3. So then we'd have 1, 3 dichloro cyclohexane. That's hard to say. All right.
Sorry.
Go ahead.
So the line in the middle on the inside is the same as if you attach the chlorine bond. Is that what you said?
The line in the middle?
Well, because there was a line. I missed it. Sorry.
Oh, like. So if I put a chlorine there,
Yes.
that immediately becomes number 1. Now, if I put a second one, so there's carbon 1, 2, 3, 4. Oh, actually I made heptane, but
Oh, I got it. Sorry, because I saw that line and I was confused about what that line was, but it's
yeah.
number.
So we just use this, just like we would with a straight chain, we would use the smallest numbers we possibly can. So yeah. So here we've got some just straight up alkanes. So without any substitution. So what do we call this one?
Methane.
Butane.
That's just good old methane. And what do
Oh,
we call this one?
octane.
Octane.
Yeah.
Now notice you can always tell an octane because it will have the formula C to the N with H 2N plus 2. Now the reason for that is every carbon in the middle of the chain is going to be attached to 2 hydrogens, except the carbons at the end, which are going to be attached to 3, if it's completely unsaturated. So we just multiply. So to find the total number of hydrogens, we take the number of carbons, N, multiply it by 2, and add 2 for the extra hydrogen. There's going to be 1 extra hydrogen at one end and 1 extra hydrogen at the other end. So that's how you know it's an alkane. Now, what do we call this?
Cyclohexane.
cyclohexane. Now, if you have a ring, on the other hand, now you don't have any terminal carbons. There is no carbon at the end. There's no carbon at that end, and there's no carbon at that end because there's no ends. So for a cycloalkane, how many hydrogens are you going to have for every carbon?
Just 2.
2. So for a cycloalkane, it's just CnH2n. Okay, which is the same, actually the same formula for an alkene. An alkene, since we've replaced 2 hydrogens with a double bond, we're going to have HNH2n. And for an alkyne, we've removed 4 hydrogens and replaced them with 2 carbon-carbon bonds. So that would be CnH2n minus 2. So we'll get into more of those as we go along. So those were simple compounds. Let's look at something a little more complicated. Now, what are we going to call this one? What's the longest stretch of carbons?
2-chloropentane. I think.
Nope.
Oh,
You're
oh, I forgot
close.
the third one.
So what's the longest stretch of carbons?
2-chloro-3-methyl pentane.
Right, pentane. So 1, 2, 3, 4, 5. So that gives us the smallest number for our substitutions. And you're right. So 2-chloro. You watched the video this weekend, didn't you? I could tell because you asked me questions about it last night. 2-chloro-3-methyl pentane. Right. So that's the first one. Now the second one is this one. What do we call that?
Methyl cyclo had pentane.
Right, there's 5. 1, whoops. There is 1, 2, 3, 4, 5. So it's cyclopentane. It's got a methyl substitution on, but since there's only one substitution, we don't have to say where it is because it's assumed it's at carbon number 1. So that would just be methyl cyclopentane. Excellent.
Please give us these simple ones for the next exam and the cumulative exam.
Oh, no,
Final.
they'll be insanely hard. So skeletal structure. So here, let's do, whoop, don't want that. Let's do A. So what's going to be my long chain?
Be 8 carbon.
How many carbons?
8.
8? Are you sure? What's my longest stretch in a
I'm
row?
sorry, not 8. Hexane is 6.
6, right, 6. So I go 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So I have a substitution at which carbon?
At 3?
At 3. And what is the substitution?
Ethyl group.
It's an ethyl group. So what is an ethyl group?
CH2, CH3.
Right, it's just carbons. And there's 2, ethyl is 2. So this one, I would just draw, let me erase this. I put one line. Oop. That tells me that's one carbon-carbon bond. And that tells me there's another one. So I would put it at an angle slightly like Let me just erase, that's kind of ugly there. So my line, let me just move this out of the way. So it'd be like this, 1, 2. So basically, yeah, just you draw it like that. So that tells me that there's 1, 2 carbons in there. So let's do B. What's my longest stretch of carbons for this one?
5.
5. Now, are they in a line or not?
No, a ring.
No. So it's cyclopentane. So 1, 2, 3, 4, 5. Man, I can't draw worth a damn. That is sad. Let's try that again. 1, 2, 3, 4. Well, that doesn't get any better. All right. So there's 5. And where are my substitutions?
1 and 3.
1 and 3. So at position 1, what do I have?
Bromine.
Bromine. And then at position 3, what do I have?
Iodine.
Iodine.
Iodine. Now I could put it there, or I could put it there. It wouldn't make any difference. So I could go 1, 2, 3, 4, 5, or I could go 1, 2, 3, 4, 5. It wouldn't make any difference at all. Just don't put them in both places, because basically they'd be mirror images of each other. Great. Okay. So, man, that was fun. Let's see if what's resume recording. All right, so the first one, I'm basically they're multiple choice. Hopefully you were able to figure those out for yourself. But as far as number 2, what did we get for the first one here for A? What are we gonna call that?
Butane.
Methylbutane.
Oh, so we got some. So methylbutane, how many carbons would methylbutane have? How many carbons would butane have? Let's start there.
4.
Butane would have 4. And methylbutane would have how many carbons? That would be butane with another methyl group on it. So how many carbons would that have?
5.
5. And how many carbons do we have here?
Just 4.
Just 4. So we've got 1, 2, 3, 4. And the question is, do any of those carbons have a substitution on them?
No, my bad.
They don't. Yeah, this is a trick. This is an evil, chemistry professor trick. So if you drew that, if you drew the Lewis structure of that, you would just have 4 carbons in a row and they would all be saturated. So there's no substitutions. So remember, carbons in the middle of a chain are going to be attached to 2 other carbons, one there and one there, and have hydrogens filling up the rest. Now, when you're looking for a substitution, look for a carbon that's attached to 3 or 4 carbons, like that one. That carbon is attached to 1, 2, 3 other carbons. So automatically we know that that's got a substitution on it, okay? So this one is just old-fashioned butane. There's nothing, so that's a dirty trick, which I am want to do. So what do we call number 2? What's the longest chain we can make with that one? Longest continuous chain of carbon atoms.
3.
3, right? And it doesn't matter if we go 1, 2, 3 or 1, 2, 3. It's this, we'll get the same thing. So 3 is the longest chain. So what's our root structure for this? What's our root name?
Propane.
Propane, right? So we've got a substituted propane. Now the question, so remember, when we finish the name, we need both the number, what carbon is substituted, and what is the substitution. So what do we, so for this one, which carbon has got a substitution on it?
Number 2.
Number 2, right? And it doesn't matter whether we're naming them in this direction or we're going in this direction. This one is still going to be carbon number 2. It doesn't really matter. So 2 dash. And what is the substitution?
Methyl.
Methyl, that's right. If that was CH4, it would be methane, but we remove one of the hydrogens and attach it to a carbon, becomes methyl. 2-methyl propane, right? All right, so number, oh, this one, people had fun with this one. So what's the longest stretch of carbons we can go into, we can make in a row?
5.
5. And it doesn't matter what direction we go, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. 5 is the number. So since it's 5, what's our root?
Pentane.
Pentane, that's right, excellent. And which carbon has the substitution on it?
Both substitutions are on 3.
Both are on 3. So since 3 has 2 substitutions, well, we'll save that for now. So carbon 3 has the substitutions. What are the substitutions?
Ethyl.
Ethyl, that's right. This is an ethyl group. And this is an ethyl group. They're both that particular group. So they're both ethyl. So since how many, so what are we going to call this? Do we call it 3-ethyl pentane? I saw that in a number of groups. Is that how we name it?
Is it 3,3-diethyl pentane?
That's right. Since both substitutions are ethyl, we use diethyl. Now remember, this just says the total number of ethyl groups in the pentane molecule. How many substitutions of ethyl are there? A total of 2. Where are they? Well, they're both in the same place. So we have to say 3 and 3. So that means the first ethyl is at 3, second ethyl also at 3. Now, if we had, we could also call this tetraethyl methane. Why could I call it that? This is also a legitimate name for that. What does tetraethyl mean?
4 groups of ethyl.
Let's read. It means there's 4 ethyl groups. 1, 2, 3, 4. And they're all substituting a single carbon. Well, what's a single carbon called? Methane. So we could also call it tetraethyl methane. And I wouldn't have to put down any number for methane because methane only has 1 carbon. So either one of those is correct. All right. So I think most people did a pretty good job with these. So pentane tells us how many carbons are in my straight chain. So pen, what does that refer to?
5 carbon.
5.
5, right. So if I'm doing the skeletal structure, I go 1, 2, 3, 4, 5. So there's my 5. And then which carbon has substitution?
3.
3. Which one's 3?
The one in the middle.
The one in the middle, right. So 1, 2, 3, 4, 5. And again, it doesn't matter which direction you go in, 3 is going to be the one in the middle. So what do I put there? What's it? How do I represent an ethyl group just using straight lines?
A straight line going down and then another line coming off of it diagonally.
That's right. So this tells me this line is a single carbon-carbon bond, and this line is a single carbon-carbon bond. So that tells me I have 1 carbon here, 1 carbon here, and 1 carbon there, which is exactly what we have. So that would be the complete structure for it. So let me erase some of this stuff. So completely, it would just look like that. And when we're doing the Lewis structure, we would just have 1, 5 going across. And then this would have 2 carbons going up, and then just fill in the rest with hydrogens. Now I've mentioned to people at the end of these are all going to be CH3. So if you get tired of just, putting hydrogens everywhere, on these terminal carbons, you can just put H3 if you want. So CH3 and then carbon, 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 and then fill in the hydrogens. But you can put a CH3 at the end if you want, because I know it's a pain drawing all of those. All right, so hexane, 2,3-dimethylhexanes. So my root is hexane. How many carbons is that?
6.
6. So I go 1, 2, 3, 4, 5, 6. And where are my substitutions?
Two and 3.
2 and 3. So I can have 2 be here, or I can have 2 be there. Makes no difference. As long as my 2 and 3, I can have 2 and 3 here, or I can have 2 and 3 there. You can draw them either way. Doesn't make any difference. As long as the 2 and 3 are next to each other, and the 2 is 1 away from an end. Doesn't matter which end, just an end. So what are the substitutions on 2 and 3?
Methyl group.
They're methyl groups, right? So how do we represent a methyl group as a stick figure?
Just a straight line.
Just a single straight line. So remember, the dimethyl doesn't mean that 2 and 3 both have a dimethyl substitution. Dimethyl means there's a total of 2 methyl groups. 2 of them total. If there were 2 methyl groups at 2 and 3, that would be 2,3 tetramethyl. Total of 4 methyl groups. But since it's dimethyl, it means there's a total of 2, 1 at 2 and 1 at 3. So you can draw it like that. You can also draw it like this if you prefer. Either way is fine. Some people like putting the methyl there, other people don't. Decide whether you're one of those people that like putting it there or one of the people that don't. It doesn't matter. Just be consistent internally. If you're going to put a methyl there, do it for all the methyl groups on the compound. So now we have heptane. So how many carbons is that one?
7.
7, right. So we go 1, 2, 3, 4, 5, 6, 7. And so where are my substitutions?
2 and 3.
2 and 3. And they're going to be different. So notice that when we do these in alphabetical order. I maybe didn't make that point very clear during the introduction. So if this was 3-chloro, 2-iodo, that's how we would write it. Chloro comes before iodo, not 2 comes before 3. Okay, it's a little weird. I mean, it should be the other way around, but it isn't. So, so 2 has a chlorine. So which one is 2?
The second one.
The second one, and again, regardless of which direction we go. So this can be 2, or that can be 2. Either way, if you're left-handed or right-handed, you may want to change that. So at 2, we have a chlorine. So how do I represent that?
Align with the Cl.
Right. We put a line. Now this is maybe a little confusing because doesn't that mean a carbon-carbon bond? Well, in this instance, it means a carbon-chlorine bond. We don't just put a chlorine hovering above it because we want to show that it's actually covalently linked. So we do use the line for that. So we use a line for any carbon non-hydrogen bond. So at 3, now remember 3 has to be right next to it. If I'm going 1, 2, 3, I can't, or 1, 2, 3, I can't put the iodine here. That would be 2, 3, 4, 5. That would be 2,5-iodo-heptane. So the iodine has to be here. Let me clear out the rest. So that would be it. And then when you're doing the Lewis structure, you just want to have 7 carbons in a row. 3, 4, 5, 6. And then you have CH3 at the end, CH3 at the end. Go away. Stupid computer. Okay. And then, yeah, so the chlorine would go, oops. Chlorine would go here, iodine would go here, and just fill the rest with hydrogens. Now for the last one, heptane again. So how many carbons?
7.
Still 7, right? 1, 2, 3, 4, 5, 6, 7. And where are my substitutions?
Carbons 2, 3, and 5.
Right. So I have one substitution at 2. I have one substitution at 3. How many substitutions do I have at 5?
2.
2, right. That's why we have the 5 twice. So, because it tells you that 5 has 2 substitutions. So if I go 1, 2, 3, 4, 5, so 2 is going to have what substitution?
Methyl.
It's going to have a methyl group. And again, there's 2 ways to put the methyl group on. I can just put a line there or CH3. Either one is fine. So there, one goes there. Another one goes there. And then when it comes to 5, I'm going to have 2 of them, right? So one going up, one going down. Or as another group pointed out, and I think this works just fine, you could also have that. That works too. Anything that shows that this particular carbon has 4 carbon-carbon bonds. So it's bonded to this one, this one, this one, and this one. So
Is it possible?
this particular carbon would have no hydrogens attached to it.
All right, is it possible to just draw a straight line?
Is it possible that what?
To draw a straight line through the 5th one?
Yes. Yeah, as long as it's above and below.
Yeah, I just drew a vertical line above and below it.
Yeah, that works too.
Okay.
So you could also draw it that way. And again, you could put the methyl here and the methyl there. Either way, there's a number of different ways to do it. Just make sure it's perfectly obvious that it's just a single methyl group and that there's 2 of them. You don't want to put a line that looks like this, because that tells you that there's an ethyl group there, not a methyl group. So we get to 4. Why is it that the first 2 have density in grams per liter, but everybody else has density in grams per milliliter? Why is that? I know you know, Vera. Who else could tell me why that is? What's the difference between a substance that has a density in grams per liter and one that has a density in grams per milliliter? What can we say about the difference in those 2 things?
Is one a gas and one's a liquid?
Bingo. Which one's the gas? Which one's the liquid?
Propane and butane.
Right.
Are liquids.
These 2 are gases. Everybody else is a liquid. And the key to this is at 20 degrees. So at 20 degrees, if you have a boiling point of -42, you are going to be a gas. If your boiling point, on the other hand, is 69 degrees, well, at 20 degrees, you're going to be a liquid. But the more important question is why? Why are propane and butane gases at 20 degrees, but the larger alkanes are all liquids at 20 degrees? Why is gasoline a liquid and not a gas? What's responsible for that? What's responsible for making things liquids and solids in the first place?
Doesn't it have to do with like the pressure?
It has something to do with the molecules themselves. Why is water a liquid? So water is a fairly small molecule. Water is a liquid at 20 degrees. Propane is a gas at 20 degrees. Why? What can water do that propane can't? With other molecules.
Does that have anything to do with it being able to be an acid or a base?
Not really. No, but I mean, you're sort of onto something with acids and bases being a different kind of molecule than propane and butane and pentane. What sort of interactions can water do that propane can't?
Polar.
Water is polar. There you go. Water is polar. So what kind of interactions do polar molecules have?
H bond.
Sorry, what's that?
Hydrogen bond.
They, not all polar molecules can hydrogen bond. Water can.
They're
Remember,
attracted.
for hydrogen bonds, you need to have oxygen, nitrogen, or fluorine attached to hydrogen. So not all polar molecules can do that. Water can do that. But polar molecules can do something else. What kind of interactions do polar molecules have? It's right in the word polar.
Was it dipole or something?
Dipole. There you go. They have dipole interactions, which are fairly strong. And hydrogen bonds are even stronger than that. They're a special, very strong dipole interaction. It's basically what a hydrogen bond is. But propane and butane and all these other alkanes, can they have dipole interactions?
No,
No. How come?
non-polar.
They're non-polar. Exactly. These are non-polar molecules. So what sort of interactions can non-polar molecules have?
LDF.
LDF, what does that refer to?
London dispersion force.
London dispersion force. Okay. So why is it that propane is a gas at room temperature, but octane isn't? It's a liquid. Why is that? If all they can do is just weak London dispersion non-polar interaction, how come octane can still be a liquid and propane can't?
There's more London dispersion forces.
How come?
That you have to break.
Why does octane have more than propane?
Have longer.
That's right, they're longer molecules, they're bigger. Octane is much more surface area than propane does. And so octane can make a lot more of these weak interactions than propane can. And the more of these weak interactions you could make, the more energy it takes to break them. And so gases, remember, don't really have any interaction between molecules. That's why they're gases. Liquids are liquids because there is strong interactions between the molecules. So even though these are weak interactions, if you get a whole bunch of them, you can have enough to be a liquid. And so once we get from 4 carbons to 5 carbons, we get a fairly, well, even going from 3 to 4 to 5, you see there's a big change in the boiling point. Here we change the boiling point by 41 degrees C, just by adding a single carbon. Then we change it by 37 degrees C. And then, each increase is a little bit less each time, but it shows you that there's a big difference just adding a single carbon, because it makes the molecule bigger and makes more interactions. So that's what we were looking for. So the change in the density is due to going from a gas to a liquid, and the reason is the increase in London dispersion force. Excellent job, everybody.